Look at that. Transformations. Yes, they are back, and they're back with a vengeance. Why? Because you could do transformations to logarithmic, listen to this word, functions. Yes, it's a function, so you can transform it. Ah, but do we have to learn a whole brand new thing? No, because look at this. Look at the formula, how it's identical. The only difference is the function. Now you're throwing a log in there. That's it. So yes, you still have stretches. Yes, you still have horizontal stretches, 1 over b. You still have translations left and right. You still have translations up and down. It's the same darn thing. And as a matter of fact, not only that, is it follows SRT. You know what was really cool about this slide? All I did was go back and just duplicate this slide from way back in the transformations unit and just change the function to, of course, my favorite, which is logs. Oh, this is so cool. So enough jibber jabber. Let's get at her. Oh, look at that first question. Oh, now check it out. Original was a log. Okay, so being that that's a log, let's go to it. So first thing you got to do, figure out A, B, H, and K, as we always do. So A, -2. B, looks like a 1 there. H, oh, that's a 3. K is 6. So describe what's happening here. Well, horizontally, there's no stretch, but we are moving. Okay, so we're going 3 to the right. Oh, that's nice. That's easy peasy. But how about vertically? Well, don't forget, this is a negative. Being that this is a negative, we are reflecting. But don't forget, your stretch is first. Okay? Your stretch is first. So we're going to stretch by factor 2. So remember, this is a vertical stretch, so I'm going to put a VS there. Okay? By a factor of 2. Okay? We also are going to reflect. And remember, when we do a reflection on a vertical, we're reflecting over the x. Oh my goodness. Over x-axis. I'm running out of room. And then finally, don't forget, we're moving 6 up. 6 up. Oh, how pretty. Okay, so let's go take a look at the transform point then. Let's pick a point, and the easiest point is this one. Now, why am I choosing this point? Because remember in exponentials, I chose 0, 1. Now, what was the reason for that? Because we were dealing with exponentials, something like 3 to the power of x. You know, if that was 0, that next number, of course, is going to be 1. And that was consistent for all the graphs out there. Being that this is a logarithmic function, which is an inverse of this, you flip these two and deal with the simplest point, 1, 0. That 1, 0 being common to every single logarithmic graph out there, except for the transformed ones, of course. Okay, so anything that looks like this will always have a point that's 1, 0 that we can transform later on. Okay, so best thing you can do at this point now, set up a mapping. Let's go. I need some room, so I'm putting it down here. Mapping notation. There's my x, y. What's happening to my x and y? Well, okay, my x, no stretch, no reflection horizontally, but I am moving 3 right. So I'm taking every x point and I'm moving it 3 to the right. Then, what am I doing vertically? I'm stretching by 2 and flipping, so that's why it makes this a -2y, and I'm moving 6 up. Okay, there's my mapping. So now if we take this point of 1, 0 now, we can throw it into there and just find out where my new point's going to be. Where is that new point where traditionally the log graph goes in here like this and goes through that point of 1, 0? Where does that point end up? Okay, well, I can figure that out. That's pretty easy. Just take the 1, 0 and plunk it into our mapping. Well, 1 plus 3, oh, that's tough. That makes this a 4. Okay? 0 times -2, well, that's simple enough. 0 times -2 is 0, right? Plus 6 makes my new point 4, 6. So I can actually go out here and put this new point on. 1, 2, 3, 4. 1, 2, 3, 4, 5. There's my new point. Let's erase the other one so they don't look like points there. That'll mess us up later. Okay, so there's my transform point. That point that was originally here is now up here. Okay, beautiful. Let's talk about a few other things. What was the, I'll give you a hint. What was the domain of our original graph? Wasn't it all values of x that have to be greater than 0, right? Yeah. Okay, because that thing is an asymptote. So I'm curious, where's our new asymptote going to go? Well, the mapping tells you. The mapping says move everything over by 3. So guess what? The asymptote, which was normally at x equals to 0, is now moved over to 3. There it is. It's moved over 3. So guess what? Your new domain is x greater than 3. That makes sense. All because of the fact that you did the mapping first. Cool. How about the range? Surprisingly enough, when you got a graph that's going like this, your range, of course, yeah, you know it. X is an element of R. Now, the equation of the vertical asymptote is pretty easy now because it's based on the domain. X equals to 3. Now, here comes a challenging part. Let's look at the X-intercept and the Y-intercept. And you're probably saying, well, why are we doing that? Because look, so far on my graph here, I only have this little itty bitty point. It really doesn't tell me too much more about the shape of this graph. I want to know more about the shape of this graph before I end up graphing it. Okay, so let's go. The equation then, if you remember, the equation up above was -2. I'm just going to rewrite it. The log of base 3, x minus 3, plus 6. That's what your y equals to. All right? Now, remember your intercepts. This is where it becomes fun. Okay? This is where you got to know your algebra and you got to know your logs really, really well. All right? So let's figure out our x-intercept right now. Our x-intercept happens when y equals to 0. Oh, okay. So that means this guy now is 0. And how do we solve this thing? First thing I would do, move the 6 over. So you got now 6, this will be -6 equals to -2 log, right, of 3x minus 3. Okay, now start doing the algebra magic. Divide by -2, divide by -2. That cancels, of course, giving us now 3 equals to the log, okay, of 3x minus 3. Now, do you remember how to solve this thing? Sure you do. You take the base, raise it to the exponent of 3. Okay, so this is 3 to the power of 3 equals to x minus 3. Well, 3 to the power of 3 is very easy. That's 27. X minus 3, bring the 3 over, you find out that your x-intercept is actually at 30. Oh my goodness. Well, okay, that's going to really help us out with this graph now. Look at this. Let's go back to the graph. We know the x-intercept is going to be way, 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 way out there, right? So now we can draw the graph. We can draw the graph actually quite nicely because all we have to do is remember that that intercept is way the heck out there somewhere, way, way out there. We can come along here. There's our, of course, our asymptote, and then we could start bending and just kind of pushing out there, way out there, and eventually it's going to cut the axis out at 30. But what do you notice about this? If my graph looks like this, do I actually have a y-intercept? Well, graphically, no. We don't have a y-intercept. But can I prove that? Well, actually, yeah. Let's do that right now. There's the challenge. Tell me what the y-intercept is going to be. We all know that it does not exist, but I want you to prove it. Okay, x equals to 0. This is going to be really easy. Watch. You want to find the y, -2. You're going to go log base 3 of 0, now it goes where the x is, -3 plus 6. Look what you end up with. This is the scary part. -2 log base 3 of -3 plus 6. And guess what? You can't do a log of a negative. That's why the y-intercept does not exist. Our x-intercept is 30, but guess what? Even graphically, we see that our y-intercept doesn't exist. Stay tuned. We got 2 more coming at you.